With the help of a mass spectrometer, we identified two major isotopes for carbon. Carbon-12, meaning 12 total nucleons, protons and neutrons, and carbon-13, containing one more neutron than the carbon-12. So let's look a little bit more carefully as to what we're talking about here, and we'll define our terms a little bit. Remember, first of all, the nucleus has a volume much smaller than the total volume of the atom. And inside the nucleus is where we find the protons and the neutrons. The rest of the space occupied by the atom is just simply electrons. Okay? Now, the difference between carbon-12 and carbon-13, we said, was one neutron. Notice that the number of protons in carbon-12 and carbon-13 are exactly the same. And in fact, the number of protons defines those atoms as being carbon. So we oftentimes will describe that in this notation here. You'll notice the C for carbon. The 12 above is the mass number. That simply is telling you the total number of nucleons, total number of protons and neutrons. The lower number, if you see a lower number, sometimes this is not there, is the atomic number, and that tells you the number of protons. Well, notice that the atomic number for both carbon-12 and carbon-13 is 6. It's exactly the same. And again, what defines these two guys as carbon is that they have 6 protons. If we put in another proton, we get a different atomic number and therefore a different element. Okay? So in addition to carbon-12 and carbon-13, we also actually have another isotope that is not abundant enough in the Earth, on the Earth's surface, to be significant to us, but it is in fact important because it's a radioactive element. The nucleus is in fact not stable. We'll have lots more to say about that later, but you may have heard of radioactive dating or carbon dating, and that has to do with the decomposition of this nucleus. And so we'll talk more about that a little bit later. But right now, again, the point is of all of these isotopes, they all have 6 protons, identifying them as carbon, and varying numbers of neutrons. Therefore, their mass number changes. When I say then carbon-14, again, I'm identifying it as carbon, 6 protons, 14 neutrons, 14 nucleons total, so therefore it must have 8 neutrons in this case. Okay? Now, when we look at when we deal with neutrons or protons, they're really small, and it doesn't make a whole lot of sense if we're talking about the mass of an individual neutron or proton or carbon atom to deal with a massive unit like a kilogram. We know a kilogram is a big, huge macroscopic thing. And so let's define now a mass unit that's more appropriate for the delicate atom or proton. What we'll do is take a carbon atom, which has a mass of 1.9924 times 10 to the minus 26 kilograms, and we're going to divide it by 12 because there are 12 nucleons in that carbon-12 atom. Why carbon-12? Why not something else? This is just a super stable isotope of carbon, and so it's very convenient to use that as a standard. But we could have chosen anything we want, but by convention, scientists have all agreed that that's going to be our mass standard. So we're going to take one carbon-12 atom, divide it by 12 nucleons, 6 protons, 6 neutrons, and that gives us then 1.66 times 10 to the minus 27th kilograms. Okay, that is our conversion factor. 1 AMU we will define as 1.66 times 10 to the minus 27th kilograms. So if we have a mass in kilograms, we know a quick way then to convert it to atomic mass units, or vice versa. Okay, if that's true, if I have one carbon-12 atom in my hand, it's going to weigh exactly 12 AMU, because we defined it that way. Okay? If I have one hydrogen-1 atom, in other words, hydrogen with just a proton in it, no neutrons, that's going to have a mass very, very close to 1 atomic mass unit. Not exactly, as we'll see why in a little bit. If I have a deuterium atom, that's hydrogen with 1 neutron, so total number of 2, a mass number of 2, that's going to have a mass of very, very close to 2 atomic mass units. If I have a tritium atom where I have a mass number of 3, that's going to be really close to 3 AMU. You get the idea. It makes it much, much easier when we're talking about atomic mass units, because that effectively tells us very close to the number of nucleons in the nucleus. That's good. Okay, well, so when we look at a periodic table then, remember that the different elements are defined by the number of protons they have. So what makes sulfur sulfur is that it has 16 protons. It's got an atomic number of 16. What makes beryllium beryllium is it's got 4 protons, an atomic number of 4. Okay? What makes nitrogen 15 different than nitrogen 14 is the number of neutrons. Just to remind you, it's still nitrogen because we haven't changed the number of protons in that case. Well, one of the bits of information that you'll see on a periodic table, again, is this number at the top, the atomic number. Once again, just tells us the number of protons. The elemental symbol, which again is dictated by the number of protons. And then this guy down here, the relative atomic mass. If carbon existed only as carbon-12, this would be the exact mass of one carbon atom. But in fact, notice that this number is not 12. It's not 12 because, as you would guess, because I just led you this way, carbon exists as 2 major isotopes, carbon-12 and carbon-13. And so this is in fact an average mass for a carbon atom, not the actual mass of carbon-12 or carbon-13. It's a weighted average of those two, given the fact that there's a lot more carbon-12 than carbon-13 here at the Earth's surface. So let's define that a little bit better. Again, what I want is a weighted average of those two nuclei, of those two different atom types. So carbon-12 weighs exactly 12 AMU. I multiply that by its abundance, 0.988. In other words, there's 98.89% carbon-12. That's going to give me this number, and I then multiply carbon-13 by its natural abundance. Gives me this number, and I just simply sum those two together, and that gives me a weighted average then of the two. Notice a weighted average is different than a simple average. If I took the average of 12 and 13, it would be 12.5, but that would not pay attention to the fact that there's a heck of a lot more carbon-12 around. So I need to multiply it by abundances so that I get a weighted average, the appropriate ratio of these guys. So again, you'll notice this number is a little tiny bit bigger than 12 because, again, there's about 1% of carbon-13 at the Earth's surface. And I'm not worried about carbon-14 here because it's just too small of an abundance. Okay, so if you actually had to do a problem, what it might look like is this. Atomic weight of an element corresponds to the weighted average of all its naturally occurring isotopes. Let's talk about neon. Neon exists as neon 20, 21, and 22. The dominant form of neon is neon 20. Okay, and again, what separates these guys is the number of neutrons, right? Okay, so you want to figure out the atomic mass for neon, and you've got to take the weighted average of those isotopes. So once again, you would be presented typically with the data for the masses of those different isotopes. If you weren't presented with them, you could go in the lab and measure them with a mass spectrometer. And then you get percentages, and again, that's something that you could get with a mass spectrometer also. You just simply collect this data, and the relative heights on the mass spectrum will tell you the abundances, and again, the mass on the x-axis, if you remember, that'll tell you the masses. Multiply abundance by the mass, and you end up adding those guys together, just like we did with carbon, and you end up with a weighted average for neon of 20.18. Okay? Now, here's something peculiar. Neon 20 has got a mass of 19.992. I'm going to add the mass of exactly 1 neutron to neon 20, and I end up with 21.000 AMU. Notice that that number is not the same as the actual experimental value, 20.993. Now, I know you can look at that and say, well, that's not a big difference. Maybe somebody just rounded off wrong or used a Casio calculator or something like that. I take it all back. I don't really mean that. In this case, the problem is not in the calculation. There is, in fact, a difference between the weight of the neon 20 and 1 neutron and the neon 21, and that difference has to do with
Answer man,
something
answer
we'll see
man,
in just a
if
moment.
you can't answer it Nobody can.
I'm going to show you one other example of this, and then we'll get to what's going on here. But again, let me just leave you with the notion that if I take neon 20 and I add a neutron, I don't get the mass of neon 21, even though we just said neon 21 is just one more neutron than neon 20. Something's going on here. Okay, it becomes even more apparent if we talk about a whole atom. In other words, let's think of a simple atom, helium-4. Okay, helium-4's got 2 protons, 2 neutrons, 2 electrons in it. Okay, well, I could take the mass of a proton, I know what that is, multiply by 2. Take the mass of a neutron, multiply by 2. The mass of an electron, multiply by 2. Add that all together, and the mass that I get is significantly larger than the mass of an actual, authentic helium atom. Okay, so something's going on. There's 5 times 10 to the minus 29th kilograms missing. Now, I know that seems like a pretty small number, but this is per atom that is missing. If I had a large collection of helium, that's a significant amount of mass that is just gone. Now, we love to think about mass being conserved. For the most part, that works pretty well. But in fact, when we're talking about changing the nucleus of an atom, mass is in fact not conserved. The reason is because of this very famous relationship that you've certainly seen before by Einstein, that energy is equal to mass times speed of light squared. Now, what that says is that energy and mass are in fact interchangeable. And when these guys come together, there is so much energy released that there is a loss of mass, released again in the form of energy. Well, put that in reverse. If you took helium-4, if you could take a helium-4 atom and break it apart into protons and neutrons, you'd have to put in an enormous amount of energy in order to do that. And as a result, the mass actually would increase. You'd get your particles back here. So because there is such an enormous difference in energy, that's called the binding energy, the energy that holds that nucleus together, and it's an incredible amount of energy. So much so that normally we don't have to worry about the nucleus changing when we're doing chemical reactions. We can leave that to the physicists. That's nuclear chemistry. We'll actually talk a little bit about that, but not for a while. We're going to just assume that the nucleus is not changing. We'll go ahead and buy into one of Dalton's postulates that the nucleus is indivisible, even though we know that that's not completely right. But that's going to be the assumption we can make. So if we do that, then energy and mass will be conserved as far as we're concerned, at least. We won't be able to tell the difference, and everything will be okay. It's only if the nucleus is changing that the energy differences are so great that the mass will be changing enough that we can actually measure that difference. So that'll be important for us to remember when we look at nuclear chemistry, but not when we're talking about chemistry in general. So, okay, where are we? Well, we've identified mass number as the total number of nucleons, meaning protons and neutrons. We've identified atomic number as being the number of protons, and the atomic number defining the name of the element. We've also said, okay, we're going to go ahead and assume now that all atoms maintain their nucleus. We're not going to worry about nuclear reactions. We're going to just consider chemical reactions, in other words, the rearrangement of atoms to go from some molecules to different molecules.